Okay, let's get started. Uh, Today we're going to talk about a paper from Humphreys and Jacobs, but before we can talk about anyone else's paper, I have to talk about the fact that this is Columbia develops Stan, the university employee, use Stan for business purposes. Any employee who has those considerations is required to disclose those facts in presentations. However, McCartan Humphreys is an employee of Columbia University, but not bound by this conflict of interest because he's not being funded directly for Stan, even though he's using Stan in his research, which we'll get to. But before we do, want to talk about an important paper that was released on the internet that pertains to this question: does the software that you are using work as intended? Which we talked about right back toward the beginning of the semester and maybe a couple times since then as the fourth source of uncertainty that you're going to have to wrestle with, along with uncertainty as to what model or what models are best for a particular data generating process. Among those best models, uncertainty about what the parameters in those models are. Third source of uncertainty, what to do with the output, how to make a decision on the basis of that. And the whole Bayesian framework handles those three things pretty well. Starting with the last, what do you do with it? Well, whenever you want to make a decision, simply write down the utility or the loss function that you're going to use to make the decision. Evaluate that loss function if you were to make this or that decision across the whole posterior distribution for all the unknowns that you have that are part of your model, and then make the decision that maximizes expected utility. So Bayesian framework covers that pretty well. First source of uncertainty, what models to use. We've talked a good bit about that. The Bayesian approach has a lot to say. First, you can sort of straight up put posterior probabilities on which model is correct, given that one among a set of models is correct. That is a pretty strong assumption to make, but you can certainly do that. Weaker than that, we have expected log predictive distribution, which model is expected to predict future data to the base, or if you're just going to say, well, if prediction accuracy is really where your utility function turns on, what are the weights that would be applied to the predictions from a set of models that yield optimal predictions with the stacking weights and so forth. And that reminds me that everybody should install the latest versions of Loo and RStanArm and BRMS and ProjPred and all that, because they have been updated in the past week or so, and they have all the functions that some of the time we were installing stuff from GitHub and things like that. It's now supported with all those things in CRAN versions of the aforementioned packages, Baseplot, RStan tools, all of those. So just should update everything. And so, there's a lot to say from a Bayesian perspective about what models we should be preferring. And, in contrast, there's not a lot that can be said from a frequentist perspective, because models are not random variables and you can't really make probability statements about them. The best you can do is fail to reject or reject a null hypothesis that one model is correct. But that, what model gets to be the null model has a lot to do with the final conclusion that you reach. Also, those, tests and things like that have very little options, and even the ones that try not a whole lot of success in finite samples, if the models that you're comparing, one is not nested within the other. So one is not a special case of another. So Bayesian approach does really well on the, the third, telling you how to analyze the results to make a decision. Good on, or at least has a variety of things you can do as to what models you should choose. Obviously, you're using MCMC, drawing from the posterior distribution, and that captures your uncertainty about the parameters in those models, and you can apply any function that is of interest to you, just plumb all those draws through your function, and you automatically get a posterior distribution of the function of interest, whether that's a utility function or whatever, and it's going to, because you plumb through all the draws, automatically have the uncertainty baked into that distribution. And so the Bayesian approach does really well on those first three, but the fourth, does the software work as intended, is something that is a little bit outside of that. There's not really a way to say, okay, here's the posterior distribution that was drawn from me, like all these draws. Can I inflate my uncertainty because I don't know whether the software worked correctly? That's not really something that is built into any software. But with Stan, we're doing as much as we can to minimize the uncertainty as to whether the software worked as intended. And when it's not, or to have warnings and things like that when it appears that it's not drawing from the posterior distribution correctly. And a lot of other MCMC approaches, you simply can't tell from the output whether the output is wrong. And so with all that said, Sean Taltz, who is an employee here at Columbia, and a bunch of other people inside and outside of Columbia, released a paper on arXiv today that shows how you can validate software that is intended to draw from a posterior distribution in one way or another. It could be how Stan does it with nuts, other algorithms, etc. And the main idea behind this is that if you draw from the posterior distribution of the unknown parameters in a model and condition on data that has been drawn from the prior predictive distribution, then the so-called posterior draws that you obtain theoretically cannot be systematically different from draws from the prior distribution that you use to seed your draws from the prior predictive distribution. And so by doing that over and over, evaluating where the drawn value of the parameters falls in your posterior distribution that you get with MCMC, is fairly simple to see whether the software that purports to be drawing from this posterior distribution is working well, or conversely, that it isn't if there's a systematic difference between the posterior draws and the prior draws, because there cannot be when you're conditioning on data that's just drawn from the prior predictive distribution. And there's a lot of other proposals out there these days that we don't talk about very much, but they try to get approximations of the posterior distribution, or approximations of the posterior mode, or some characteristic of the posterior distribution, without doing MCMC, and obviously without doing analytical solution. Most of these are based on optimization in some form or another, and most of these don't work, and most of the people who are advocating things like this don't know that they do work, but that doesn't stop them from being advocated. So you have to be careful, you have to be skeptical whenever another NIPS paper comes out saying that we can do Bayesian inference really fast without actually doing anything Bayesian like MCMC in order to make inferences. And those are usually going to be lacking on one or more of fully capturing the uncertainty across models, parameters within models, how to coherently deal with the the results that come out, assuming they're correct, in order to make a decision, and you know, inability to show whether the software that they're you know, advocating works or works in general. And so it's not so difficult to show that any particular algorithm can work on some data set. Like there exists a data set in which almost every procedure that anybody could dream up isn't that bad. But that's really a problem from this sort of machine learning perspective, is that you can't really rule out any particular supervised learning algorithm, nor can you say, oh, this one is going to work on my data set just because, you know, it worked on the wine data set or the, you know, iris or something like that. And so with this proposal, it really, you can build this into your workflow. You can take the data that you have, draw from the prior predictive distribution, fit the model, and verify that the software, you know, whether it's Stan or anything else, is working as intended for that data set. And once you had that, then you're ready to proceed, conditioning on your actual data rather than data drawn from the prior predictive distribution. So most of these things don't work, and we don't talk about them. But one that does work, even though we haven't talked about it yet, and it works reasonably well for a fairly large class of models, inclusive of a lot of the things that our StanArm can do, is so-called integrated nested Laplace approximations, which uses multivariate normal approximations in order to integrate out a lot of parameters that are group specific or something like that, get a small number of parameters that are left, common parameters, that you have to get the posterior distribution of, and that can be done with a fair degree of accuracy and really quickly. And that's the so-called INLA approach. There is a R package. It's not on CRAN, but you can install it. And there's a whole book about this approach that is online in the Columbia Library that you can get from this link. But Dan Simpson, who's one of the, not the only one, but one of the main developers behind the INLA package, has since become a Stan developer. And a lot of these ideas about Laplace approximations will probably make themselves into Stan at some point, or into our StanArm, probably before they make themselves into Stan as a whole, because this is something that doesn't work too bad, and it's actually shown to not work too bad, although not perfectly, because it is an approximation in this paper by Sean. So you should definitely check that out and incorporate it into your workflow when you're, you know, saying, you know, is Stan or whatever going to work on the data set that you are currently trying to investigate. Becca. Is INLA just faster? Like, what's the value of it? Because it integrates out, or approximately integrates out, well, it integrates a bunch of parameters out approximately correctly. And so you're left with a posterior distribution that only has like 3 parameters instead of like thousands or whatever, if you have all these like group specific or geographic specific things. So it gets all rid of those, and then what's left is a lot faster. Other questions? Salisha. Yeah, I'm still not sure. What does it return? What does INLA return? So yeah, so it gives me like something like posterior. It gives you draws. So there's a sampling component coming on. Those draws are not from a Markov chain, so they are independent of each other. It's just they're only approximately draws from the posterior distribution that you might define, because the approximation to the integral it's doing to integrate out stuff that can't be integrated out exactly analytically, but can be approximately integrated out using normal distributions. And I see those draws, and I realize, oh, this works with INLA, so it's probably doesn't work with that one. Like, how do I know? Oh, so no, regardless of what software you're using, you should incorporate these ideas. So draw from the prior predictive distribution, feed that back into whatever algorithm you're thinking about using. Do that a lot of times. follow the steps in the paper. It's not too hard. And you can see, are there systematic differences between the posterior jaws and the prior jaws? And if so, the software is not working as intended. With Stan, it probably will, provided you're not getting warnings about divergent transitions, low Bayesian fraction of missing information, other things like that. But you should check. It doesn't hurt anything to check. But it goes without saying that you have to be able to draw from the prior predictive distribution, which is to say you have to have a generative model in the first place that you can simulate from. And a lot of approaches, a lot of people doing empirical work out there don't have a generative model for how the data are being generated, and thus they wouldn't even know if the software could be working correctly. So just a recap of some of the important points, in my opinion, from the presentations on Tuesday. The first presentation by Greg Warrow about the employment discrimination cases. What I think is important about that is that he's using Bayesian methods even in a situation where the treatment is actually perfectly randomized, at least within offices, sub-district offices. They're literally randomizing which judge gets which case with with a computer. And so you're in a situation in which you have ignorable treatment assignment and all things like that. But rather than using Fisherian interest with inference, is using Bayesian, because that really gets at the unknowns that he is interested in. When doing that, there's a two-part model. So one of the good things about the Bayesian approach is that it's easy to combine different sources of information. So he has two endogenous knowns that his model is trying to explain. First is the case ruled in favor of the plaintiff or not. So that's sort of a binary yes or no thing. And if so, how much money is the plaintiff awarded in the district court, and the logarithm that is being modeled with a normal distribution, etc. And with the Bayesian approach in a model like that, you can ask questions like, what if a different judge heard this case? How would we predict what would happen? You just draw from the posterior predictive distribution after using Stan to obtain the posterior distribution. Shira Mitchell was talking second about the Millennium Villages project. So this is one where they decided to do the evaluation or plan out how they would do they decided to come up with a plan how to evaluate it after the program had already been in the field for several years, and so didn't have the opportunity to build in the evaluation into the research design itself, but is still using Bayesian methods even after matching on observable characteristics for the villages in the Millennium Village project and similar villages in the same country that were not part of the Millennium Villages project. So this is another thing where sort of a lot of people in the social sciences would say, okay, we've done matching. Now let's do something like design-based inference. And in fact, in the paper, they did that as well. But Shiro was talking on Tuesday, emphasizing the Bayesian results where they're modeling several outcomes simultaneously using a multivariate normal distribution. The mean vector, it didn't depend on x's, it just depended on treatment and some country indicators, some other things like that, and then decomposing the unknown covariance matrix for those 8 or 9 different outcome variables that were being measured pertaining to poverty and nutrition and stuff like that. The covariance matrix, 8 by 8, 9 by 9, something like that, was being decomposed into standard deviations and a correlation matrix, and even the correlation matrix was being decomposed into a Cholesky factor, which is utilizing this idea of splitting things up into small parts that you can reason about more easily when specifying priors and things like that. Daniel?
So if we were to think that the matching was perfect here, what's the correct inference that makes the Bayesian is close to 5%. We think that there's correlation between prediction effects across outcomes.
Yes, so you're getting more efficiency by considering the outcomes simultaneously. And that was important because there weren't like a ton of villages being studied, and the treatment was being applied at the village level. Obviously, the villages are going to have, hundreds of or maybe thousands of people in them. But the treatments were all, and the outcomes were being evaluated at the village level. So they really only had like a few dozens or so observations, and it's important to take as much of the information, handle it as well as you can, and that involves, in her case, modeling these outcomes simultaneously, just because we think poverty and nutrition and like infant mortality and all these things are going to be, for the most part, positively correlated.
So instead of like that, you could just create like an index, right, for all the outcomes basically, but then with that in the frequency where you just have less power doing that.
Yeah, in frequentist terms, it would be, the index is not going to have like perfect fidelity to the full information. So you're going to be losing some stuff there. Also, in the paper, they didn't go so far as saying like, okay, here's what the UN should do. But if there was sort of a policy utility function on whether the program should be expanded or continued or something like that, it would be sensible to consider a loss function and do expected utility maximization to make that decision. And then finally, Sean Taylor from Facebook, using Bayesian methods even in a business setting. Now that is still something that is relatively rare. Because of the perception of not just like Bayesian statistics, but statistics in general, inclusive of frequentists, is seen by a lot of people in business settings as, academic disputes, testing hypotheses about theories of, how data are, generated. And we'll get into that a little bit with the Humphreys and Jacobs paper in a second, but, not really seeing the applicability of statistics or statistical inference in a business setting where they don't really care why, they just want to be able to predict stuff, be able to predict revenue, things like that. But Facebook is using it like RStanArm. The profit package comes with a pre-written model for doing something, in the case of profit, for predicting data of a time series nature. It was primarily, or at least originally, intended to be used within Facebook because they have a lot of prediction tasks that were not well suited to conventional tools. Also, the profit code, if you look at it, it's utilizing a whole lot of smooth functions rather than just assuming everything is linearly related to everything else. All the parameters are constant over time, which is the sort of thing that you would tend to get from most of the off-the-shelf software. So 3 different applications, all using Bayesian methods, all using Stan, all being customized to the problem that they're intended to solve, and all working better or likely to work better than the closest thing that you could have come up with if you just sort of Googled as like what's the most appropriate already written thing out there for us to use. And obviously, with Facebook, they certainly have the personnel and the resources to really dig into what is the best thing for them to use, and they came to the conclusion that that was Stan, at least for these sorts of time series tasks that they're doing. So questions about Tuesday? All right, so Thursday. So we've been talking a lot each week as this semester has gone on. That basically frequentists and Bayesians have been beefing with each other for going on 100 years now. But the real controversy within a lot of social sciences is not so much the divide between Bayesians and frequentists, or Bayesians and, you know, design-based inference people, but it's between qualitative and quantitative researchers, and quantitative and qualitative research designs and research strategies. Political science has certainly been that way since when political science first started to become a thing. Of course, that was, I guess, in the original days, I guess we kind of see that as quantitative, but they didn't really have a whole lot of data. And so it had a little bit of some of the large end, some of the small end things. But you still have that divide within and across a lot of political science departments still today. Psychology can definitely be a lot of the same way. The psychology department here at Columbia is almost entirely not quantitative, doing sort of a lot of very small data, research intensive sort of more qualitative methods on those. At least the faculty, some of the graduate students are doing quantitative research. Of course, within economics, certainly, you know, 80–90% of that is going to be quantitative, where it goes kind of the other way with sociology, but you get very sharp divides between economists and sociologists to the point where it's, you know, basically a waste of time to go to some panel that includes both economists and sociologists, because it's just going to be a mess. Anyway, Humphreys and Jacobs, the paper came out in 2015. I believe it was the first paper using STAN to appear in the American Political Science Review. Works out the implications of Bayes' rule for combining quantitative and qualitative research strategies, and and that was done in STAN. It would have been hard to do prior to STAN, even though sort of the theory of it wasn't particularly novel from a Bayesian perspective, although it was worth, you know, writing up and you know, putting together for political science audience that may not have been so familiar with the Bayesian theory. But this would have been hard to do prior to STAN, because the model that they derive doesn't have full conditional distributions that are known in closed form. So you couldn't have done Gibbs sampling for everything. You'd have to fall back on some stuff like Metropolis, random walk Metropolis Hastings, something like that. But you've got a lot of inequality constraints going on, and, you know, not normal aspects to the posterior distribution that would probably make it not work well to do one of these random walk Metropolis schemes. And so, you know, even though all the pieces for a paper like Humphreys and Jacobs had been, you know, out there for a while, nobody had exactly said it in this way. And I think a lot of that has to do with people really only invest time and effort to build models that they think are feasible. And so you see things like this popping up after there's been some sort of technological innovation, such as the development of STAN, that enlarges the set of what's feasible or conceivably feasible. And then they go back and reevaluate, and then, you know, you see papers such as this one. So we'll go through that one today. Humphreys and Jacobs uses a framework that is very similar sounding to the principal stratification framework proposed by Don Rubin and some of his co-authors. So just simplifying this to the easiest case, where you have a binary treatment variable X and a binary outcome variable Y, we can think of 4 types of units that we could conceivably collect data on. Type A, which are people, or it doesn't have to be people, but units that are adversely affected by treatment. So if x is 1, then y is going to be 0. And if x is 0, then y is going to be 1 for that unit. And so it's sort of going the opposite of the intended direction of the treatment effect. Type B, units for whom treatment is beneficial. Here, y is the identity function of x. So if x is 1, y is 1. If x is 0, y is 0. Then we have type C, units that are chronic. Irrespective of what x is, y is going to be 0 for those units. And the fourth type, type D, the unit is destined. So y is going to be 1 irrespective of what x is. And so those 4 types of units exist in some proportion in a population that we're interested in studying, but we don't know what type a particular unit is, whether they're A, B, C, or D. Now, if we observe X and Y data on those units, we can rule out some things. So if X is 0 and Y is 0, we know that the unit is not destined because Y was 0, and if they were destined, Y would be 1. Moreover, we know that they're not adversely affected by treatment because we saw, well, X is 0 and Y is 0, whereas if they were adversely affected, then when X is 0, Y would have been 1. And so if we observe X and Y data, we can eliminate for any unit of observation 2 of the 4 possible types that the unit could have been, but 2 remain. So even if we observe X is 0 and Y is 0, then the unit could be type B, unit for whom treatment would have been beneficial if X had been 1, but they were in the control group, so they ended up being Y is 0. Or it could be a unit that's chronic, a unit that would have had Y equals 0 irrespective of what X is. We just happen to observe what happens when X is 0. So they might have just always been Y is 0, and thus this particular unit, the treatment wouldn't have been helpful to, even if they had been X equal 1 instead. And so same thing, if we observe X equals 0, Y equal 1, we can rule out B and C, but the data are consistent with the unit being type A or type D. If X is 1 as Y is 0, then they can't be beneficial or destined, but they could be adversely affected or chronic. And finally, X1, Y1, they could be beneficial or they could be destined. We can't just tell from the X and Y data which it is, but we could eliminate A and C. And so you can see in these 4 cells, each of the 4 types appear twice. So we have B over here, D and D, A, C, C. So each of the 4 types appear twice in the 4 cells. And so the X and Y data alone are not going to be sufficient for, saying what type of unit we're dealing with in any particular case. Questions about that? Okay. So for large volume data or data that comes with low marginal cost, often, large N data, just to be colloquial about it, can be used. So if we posit a simplex vector, which contains the proportion of each type J, in the population of interest, so this is a simplex vector of size 4, then we can conceptualize the average causal effect in this population as lambda B minus lambda A, which is to say the proportion of units that are beneficially affected by the treatment minus the proportion of units that are adversely affected by the treatment. Lambda C and lambda D don't go into the average causal effect explicitly because those units are either chronic or destined, and their outcomes are not being affected by treatment. And so they're just like indifferent to whether they're treatment or control. So lambda B minus lambda A is the average causal effect that we're seeking to estimate and indeed update our beliefs as to what that difference is. Then if we have another vector, which is not a simplex vector, but rather a vector of probabilities that do not add up to 1 in pi, such that pi j is the probability of observing that x is 1, given that the unit is of type j, and there are 4 types of units A, B, C, and D. So in that setup, the likelihood for data like this is just multinomial, and that is proportional to the product over the 4 types of w raised to the power ni. Ni is the number of cases where you observe x equal 1, and the corresponding probability is given by w. And so if we want to work out the probability that you are x equals 0 and y equals 0, so this first w here, that corresponds to the probability that you are type B or type C. These are mutually exclusive, so we can use the simplified form of the general addition rule. We don't have to worry about them both being true simultaneously in this setup. And so the probability that you are type B or type C can be written as the proportion that are type B in the population multiplied by 1 minus the probability of B. So again, this pi B corresponds to the probability of observing x equal 1, given that you are type B. So conversely, the probability that x is equal to 0, given that you are type B, is 1 minus pi B. So overall proportion of type B in the population multiplied by the probability of x equals 0, given that you are type B. So that covers the first part, plus the proportion of type C in the population multiplied by the probability that x equals 0, given that you are type C. And we can do the same for the rest of them. So probability A or D, that's the one in the top right over here, x equals 0, y equal 1. That has a similar construction. And then we get the probability of x equal 1, y equals 0. That means you're adverse or chronic. Those are a little bit simpler, just the proportion of A multiplied by the probability of x equal 1, given that you're type A, plus overall proportion of type C multiplied by the conditional probability of x equal 1, given that you're type C. And similar in the last cell here, probability of x equal 1, y equal 1 can be written as the sum of these things. And this, by construction, is a valid simplex vector. If you sum this all up, you get exactly 1, and thus it's suitable to feed into multinomial likelihood for the 4 possibilities of x and y. Questions there? Becca.
How do you basically what you do the inverse of pi b and pi c in the first element?
Complement? Yes.
Oh, yeah, sorry. Yeah.
Right. So pi b is the probability that x equal 1, given that you are type B. What we're interested here in the top is the probability that x equals 0 and y equals 0. So that is the probability you're beneficial or chronic. Probability of beneficial times the conditional probability that x is 0, given that you're type B, and going on from there. Other questions? All right, so all we're doing is constructing the simplex vector that goes into a 4-dimensional multinomial for the 4 possibilities of x and y. But, you know, since we don't know these parameters, we have to estimate them, and they can't really be estimated because of all the different possibilities from observational data alone. All we can do is sort of express our beliefs about them and then update them in light of the data to make sure the data aren't contradicting our beliefs, but it's still really you know, just a manipulation of our beliefs, and that's not necessarily the most convincing way to make a causal claim in the social sciences. So Humphreys and Jacobs goes on from there to try to incorporate a lot of the stuff that is done under so-called qualitative research designs, process tracing, other names for basically the same thing, which is to get a lot of information about particular units of observation. And the process of gathering that, like a lot of information about a unit of observation, takes a lot of time, money, expertise, particularly if you're talking about going to some country that, you know, they speak a different language. You have to get your language skills, these sorts of things. So for those of you who are, you know, not really in the social sciences, it's common, really, for grad students or, you know, professors on sabbatical or whatever to just pack up and leave and go to some place that I've never heard of and stay there for 2 years, and then they come back and you're like, okay, you know, are you ready to do your dissertation and stuff? Like, you know, what are your data? And they have like a journal. But that is like very common, you know, research design, and they do get a lot of information from interviews and stuff like that about the data generating process in that, you know, particular country or village or, you know, whatever it may be. But that is not something that scales particularly well. So if it takes you like 2 years to accumulate the necessary information for 1 unit of observation, you know, you could spend your whole lifetime and still, you know, not get a data set that is that big in the sense of N, but it is big in the sense of having a lot of information. So what Humphreys and Jacobs advocate, building on what a lot of the process tracing and qualitative research design literature advocates, is collect a clue, which is labeled K. We'll also think of this as binary, and or seeking clues for a simple random subset of the data that you have X and Y information on in a fairly low cost way that you know could have used the previous thing. So these clues are governed, their data generating process, by the fees. So phi jx is the probability of observing the clue, given that the unit is of type J and that their x is either, you know, 0 or 1, whichever it is. You already know that. And so these fees, there's 8 of them for the different combinations of the 4 types and the 2 values of x and y. And the so-called probative value of the clue is the difference in 2 of these fees when the type varies, but the x is the same. So phi bx minus phi dx is the probability, you know, for someone whose x is 0 or 1, whichever it may be, the probability of observing the clue given that they're type B minus the probability of observing the clue given that they're type D, implicitly keeping the x the same. And so these clues are, you know, conditional probabilities that again depend on the types. They don't explicitly have to be additional outcomes, but they could be. In any event, they are endogenous knowns at least for the units of observations where you seek the clues on. Also implicitly, or not even implicitly, it's explicit in the paper that they're assuming, at least in this initial setup, that if you seek the clue, you'll be able to conclusively say yes or no that you found it. So there's no sort of situation in which you like look for the clue for like 5 minutes. You don't find it, but it doesn't mean it wasn't there. So when we say, you know, K is 0, K equal 1, we're assuming that that's sort of conclusive if you sort of spend enough effort. Now there are 8 possibilities depending on X, K, and Y, but we can do much the same thing using the rules of probability to build up a simplex vector of size 8, the values of which are non-negative and sum up to 1. Again, just using multiplication rule, addition rule, and these conditional probabilities. So we're not going to do all 8, but maybe we'll do like one of them. So let's say the probability of observing X equal 1, K equals 0, and Y equal 1. So here we have to worry about whether you're B or D. So the probability or the proportion of B in the population multiplied by the conditional probability that X is equal to 1, given that you are of type B, multiplied by the conditional probability that K is equal to 0, given that you are type B and your X is 1. But for a unit where we observe X equal 1, K equals 0, Y equal 1, there's also type D possibility, proportion of D in the population, conditional probability of X equal 1, given that you're type D, and conditional probability of K equals 0, given that you are type D and your X is 1. And you can do that for all 8, build them up. Now you have a simplex vector of size 8 that can be used in a multinomial likelihood for the subset of observations in which you have K, data on K in addition to data on X and Y. But that's just going to be a subset because it's too costly to be, you know, collecting K for all of the observations in a lot of cases, a lot of situations. Also, the assumption here, at least to start with, that the observations that you seek clues on are a simple random sample from the observations where you have X and Y data. Like you go to that country, but only for a randomly selected subset of countries that you could go to where you have the X and Y data. So questions about that? Sebastian.
Yeah, I was kind of confused about that assumption. Well, I know,
Would not happen in practice.
I mean, that's true too, but like, you're trying to estimate something impossible anyway. So.
Yeah, I wouldn't necessarily call it frequentist, but I would say it's more of like a baseline case rather than something that is what qualitative researchers actually do. So that I would say in reality, they tend to go to places where they think they're going to find the clue or, you know, something like that, rather than choosing a simple random subset. You could conceivably enlarge the model to include, you know, probability for going to that case and seeking the clue and deriving the posterior distribution. So this is not the final word, but it's hard enough to just understand this kind of idealized baseline in order to sort of understand how these qualitative and quantitative research designs could actually be joined together.
So I think it's more about like these cases are represented.
Yeah.
So for example, the elections, like this election is representing other elections. It's not
right. Yeah, so I would say kind of in this situation, the populations are small often. So like an example in the book was like, you know, wars or you know, something like that. Like historically, there haven't been like that many big wars that, you know, you might want to study or things like that. But anyway, yeah, it's kind of, you can enumerate all the units that have X and Y, and you know what X and Y are, and then you just have to seek K for some subset of them. So this figure 1 from the paper shows how the clue stuff works and the probative value of the clue things work. So on the horizontal axis here, we have phi d for some x, whether it's x equal 1, x equals 0, the probability of observing the clue given that you're of type D. And then over on the vertical axis, we have the corresponding probability of observing the clue given that you're type B among two units that have the same value of x. So along the diagonal of this, the clue has no probative value. The difference between phi B and phi D is 0 along the diagonal line. And so observing k equal 1, observing k equal 2 doesn't provide you any information on whether this unit is of type B or type D, even probabilistic information. But if you get off the diagonal, then you can do stuff that is more interesting. The so-called doubly decisive, they're divisive as well, tests happen in the top left and the bottom right corner. So in the extreme case, if you had, phi D equal to close to 1, phi B close to 0, and then if you observe K, that is actually really strong evidence that the unit is of type D, and if K is absent, K is 0, that is really strong evidence that the unit is of type B. It's the other way around in the upper left corner, but these doubly decisive ones are clues that have like maximum probative value. You can get some kind of intermediate stuff like around here, where you're a little bit off the diagonal, but not so much. The so-called hoop test. So if K is present in this area, like that's something that you would think, okay, if the unit is of type D, then this clue really should exist. And so it's more like, does it, jump through the hoop? But the fact that it's K equal 1 doesn't really provide strong evidence that you're not type B. It's sort of just a necessary, almost necessary condition for being type D. Whereas in this situation, if K is absent, then it's very unlikely that the observation is of type D, and it's a so-called smoking gun for type B, indicating a very high probability that the unit is of type D. And it's a symmetric deal here. But anyway, you get in different regions of this plane different probative values and different implications for what you would tend to conclude, given that K is either present or absent when you go to find it. But unless you're, all the way out here, all the way out there, it's not as if you have probability 1, like absolute certainty of these things. Going back to what we were talking about, like the first week, all of these are really just, probabilistic tendencies. And so, by observing enough of them, we can say, the probability, posterior probability of this, is this or that, but we're usually not going to be entirely certain about any unit, much less a bunch of units. And so we have to use probabilistic inference. And so turning to the stand code, which is just a little bit modified from the stand code in the appendix of the paper, which was written by Jasper Cooper, who was in this class 2 or 3 years ago and is now a research assistant for McCartan, just like everybody else. anyway, when at the time there was no functions block, or maybe we just introduced it anyway. So it wasn't used in the paper, but it certainly could be to construct these W vectors for the cases where you don't have clues, like this one, or the case where you do have clues, like this one, and it's going to be of size 8. You want to expose these to R, make sure they're working correctly, give them some test values, and make sure the result is actually a simplex vector. But once you've done that and are assured that they're working well, then you can call those two functions when necessary. So the data and the transform data block might look something like this. We have multinomial data, one of size 8 for the observations where we sought clues. So the count of the number of times x equal 1, k equal 1, y equals 0 is going to be one of those 8 things, and enumerate all those possibilities. You have it there. Then we have a shorter integer array of size 4. These are the units that we have x, y data on, but we did not seek clues for those. Then we have stuff, hyperparameters that go into the priors. So alpha is the shape parameter vector that goes into the prior for lambda, which is the simplex, the proportion of type A, B, C, D, etc., or A, B, C, D, that's it, in the population. And then there's a bunch of things, the pi's, the phi's, phi 0, phi 1, that in the paper they suggest beta priors for, because these are probabilities, but they're not constrained to be like adding up to 1. Now, one of the things the paper didn't do so well is to go into how you might choose beta priors for clue probabilities, or the type B probability, whatever. And the audience that they're trying to reach is not an audience that is extraordinarily comfortable specifying the shape parameters of a beta distribution. And so if you were to go to qualitative people and say, what are your beliefs about these things, you start talking about like shape parameters of the beta distribution, you're probably not going to get very far. You have slightly better odds if you go in saying, okay, what is your best guess as to the probability of being type B given that x is 1? What do you think is the over or under value for those probabilities, to pin down prior mode, prior median, and then translate that into the shape parameters of a beta distribution, like we've done several times, going back to the Ebola example. But anyway, in the transform data, we're just taking the modes and the medians that we ostensibly elicit for the situation, and then translating it into the A's and the B's for the hyperparameters of a beta distribution. For the pi's, the conditional probability of x given that you're of whatever type, the phi 0, the probability of not observing the clue given you're of this or that type and your x is 0, and then the phi 1s for when your x is 1. And it's just using the expressions that we came up with before to map the mode and the median to first shape parameter, second shape parameter. And then we can use these when we get to the model block, which is here. So first we have to declare our parameters. Lambda, which is the simplex, automatically constrained to be non-negative, add up to 1. Then we have pi, phi 0, phi 1, which are constrained individually between 0 and 1, but there's no constraint on their overall sum. So for this, we're going to give the prior that I cannot pronounce. For pi, phi 0, phi 1, we're going to be using beta priors using the shape parameters that we constructed in the transform data block. So prior, 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 prior. And then when we get to the likelihood, in this for the cases where we have x and y, but we did not seek the clue data, we call the wxy function that we wrote in our functions block to create that simplex vector of size 4 to go into the multinomial likelihood of this. And then for the subset of observations where we have data on k in addition to x and y, we call the other function, which makes the longer simplex vector of size 8 because it takes in the phi 0 and the phi 1. So this is an example of using user-defined functions in order to, one, test that they're working correctly when we expose them to R, but also to make our model block clean looking, and you can fit the essence of this on one slide, including the generated quantities block where we calculate the posterior distribution of the average treatment effect as the difference between the proportion of type B, or beneficial, minus type A, who are adversely affected by this treatment. And so really the object of interest is this average treatment effect. In a lot of Stan models, you will find that the thing of ultimate interest is often a generated quantity or a transform parameter rather than something that you just declare in the parameters block, because of what's ultimately of interest is a function of the parameters, not just the parameters themselves. Questions about that, Sebastian?
How did the sort of two separate functions of W, X, Y, and W underscore, they're both producing lambda. I guess I don't understand how they combine to get one vector.
They don't combine.
Okay.
So you call them separately. But the likelihood combines, or the log likelihood, just by adding these two. So we have multinomial log likelihood for data where we don't see clues. And this is a simplex vector, it evaluates the size 4. And then multinomial log likelihood for the other observations where we did seek the clues. And this function evaluates to a simplex vector of size 8. But they're two different functions because for this one, we have to consider the fees and condition on those. And the first ones where we don't have the clue data, there's no fees. It's just pi's and lambda that comprise the 4 elements of that simplex.
So what are if the effect is supposed to lambda be like a proportion of fees in the population, like what's their population for this?
Yeah, so the lambda has the marginal proportion of type A, type B, type C, type D. So what we're really interested in is lambda 2 minus lambda 1. But in order to get a good posterior distribution on lambda and consequently posterior distribution on the average treatment effect, we also have to be estimating the posterior distribution of the pi and the phi 0 and the phi 1, because those all go in to the likelihood of all the parameters evaluated at the data that we have. So there's no sort of analytical way to integrate out phi 0 and phi 1 to just leave lambda, even though that's the thing that we're mostly of interest. We have to get the joint posterior distribution of everything in order to get the marginal posterior distribution of the one thing that we're most interested in. Other questions? Yes, Melinda.
The target variable in the model block, does that not need to be like predefined?
No, so it's initiated to be 0. Essentially, it gets changed because of the Jacobian transformations. And then we're just adding to it because the numerator of base law, when you take the logarithm, it becomes the sum of a bunch of logarithms. So we just keep tacking on pieces to it, prior for this, prior for that, likelihood of the parameters evaluated at the data, one piece at a time. If we didn't take the logarithm, then this would be multiplicative, but we do the logarithm for numerical reasons, also to line it with the Hamiltonian stuff from physics. Other questions? Okay. So moving on a little bit, this actually wasn't a hierarchical model, but you could make it into a hierarchical model if you had groups of observations where you thought the data generating process exhibited some heterogeneity. But it would just think about it kind of a generic hierarchical model where we have a group-specific parameter, even though I used J before, this is like a different J, just indicating group membership. Theta has some normal prior with an unknown mu and an unknown sigma. And so for hierarchical models like this, they can be difficult for nuts to sample. From them efficiently, you may get a lot of warnings, and that's because the second derivative of the log posterior kernel, it's not close to a constant. And so in order for Stan to deal, it would have to take really small steps. When its steps aren't quite small enough, you can get divergent transitions, and this is often characterized by thinking about how one parameter is affected by another parameter. So if sigma, or the proposal for sigma, is near 0, then all of the theta j's have to be very close to mu. And if any of them is like a fair amount of distance away from mu, then the posterior kernel, the log of it, is quickly going to approach negative infinity. And so you get a whole lot of curvature to the posterior kernel. And if you're dealing with something that has a whole lot of curvature and you're going through it with steps that are too big, which is to say you're going too fast, you can easily fly off the surface in with a little bit of numerical error, and you get a divergent transition. Conversely, if the proposal for sigma is large, and in a lot of times with the hierarchical models, sometimes the proposal for sigma is going to be small, sometimes it's going to be large, because we have a lot of uncertainty about these top level common parameters. And so there's a decent probability it could be really small, a decent probability it could be really big. And if both of those happen over the course of the draws, then Stan can get into trouble. So if sigma is large, then any of the theta j's can be far away from mu. You would have to take big steps in order to get out into the tail. And so you end up with a posterior kernel where in some parts of it you need big steps, and in other parts of it you need small steps. But Stan has to come to a consensus on a single step size, at least for each margin in your posterior distribution. And so if sometimes it needs to be small, sometimes it needs to be big in the same posterior distribution, it's probably going to average to somewhere in the middle, which is not small enough when it needs to be small and not big enough when it needs to be big. And you can get warning messages when either of these happen. And this can be plotted and seen after the fact. Any plot of log sigma versus the difference between theta j and its mean would look like a funnel. It would look something like this. Here, that should be sigma. The logarithm of sigma over here. Here we have the deviation between theta j and mu. So when sigma is really small, which is to say log sigma is like -10 or something like that, the theta has to be really close to its mean. So, in here, somewhere like that. But occasionally we get realizations of the posterior distribution that are, all the way down here. Whereas if sigma is bigger, log sigma is going to be bigger, then we get a lot more spread out horizontally where there's posterior mass that we have to, explore, something like this. But it's very hard to get a single step size that navigates through a funnel in a plane without losing numerical accuracy and getting divergent transitions and lots of warnings and stuff like that. So what can you do when you get such warnings? You can do reparameterizations, particularly with the normal distributions that we talked about before, because they're in the scale location family. So instead of writing target plus equal normal theta given mu and sigma, where theta is a parameter, instead you can write target plus equal normal, lambda 0, 1, so standard normal prior on lambda, where lambda is the thing that you declare in the parameters block, and theta is a vector of size j that you declare in the transform parameters block, that's constructed as mu plus sigma times lambda. And so due to the scale location property of the normal distribution, standard normal beliefs about lambda imply general normal beliefs about theta, which is the same beliefs that you had before. But now you've separated this out so that if sigma is small, theta is automatically going to be close to mu. And if sigma is large, then theta can be a good way away from mu. And none of that has any real bearing on lambda, which is, just has this standard normal prior. And so this is, Shira referred to this as the matric or the non-centered parameterization. Is something that RStanArm and BRMS do a lot of with, kind of behind the scenes in order to reduce the number of warnings, increase the effective sample size, increase the rate of convergence, all those good things. And so when you look at BRMS code, you are likely to see stuff like that. So last thing for today, when you can use BRMS to help you write your own STAN program. So you don't have to start writing a STAN program with a blank text file in RStudio. You can use the make_STAN code function in BRMS to look at or to modify the code that BRM generates. And so you can use make STAN code to get a template STAN file for the model that's closest to the one that you want to estimate, save that, and then start editing it to make it correspond to the model that you actually want to estimate. Similarly, you can use the make_STAN data to get a named list of our objects that you might add and subtract onto in order to pass that to the data block of the STAN program. And so make STAN code, make STAN data, they both take in the same arguments as BRM, or at least the first few. So here is a Poisson model. We have some counts. We have some group specific parameter by patient and by observation. These are patients that are observed over time. We have some common predictors that have common coefficients here with the interaction term, etc. We have priors. Anyway, we call make STAN code. We call make STAN data. And the list of data that make STAN data makes has this structure. So you see the N, the Y, the X, etc., and a couple of Z vectors that pertain to this patient-specific and observation-specific deviation and the intercept that we specified there in the LME4 style. And so this is the structure of the data that needs to get passed to the data block of STAN. And if you look at the generated STAN code, I had to put this in 2 columns, and so some of it gets a little bit cut off. But the STAN code, not only is it like syntactically correct, but it comes with comments that you can look at to understand, what's going on for the code that was generated. So here's the data block. Here's the transform data block where they're centering the columns of X. Here's the intercept with intercept relative to centered X's. You have some matric non-centered parameterization things going on here where we have Z1 and Z2 that are going to have standard normal priors. Z2 got cut off, but you can see Z1 has a standard normal prior. We're scaling it up by the standard deviation of the cross-patient standard deviation in intercepts, assigning that to R11, do the same thing for the observation-specific one. And then when it goes to build up mu, it first multiplies the centered X by the common coefficients, adds on the intercept, and then loops through all this and then the Z's here basically contain the interaction between the group level indicators here, the patient or the observation, and these sort of deviations in the intercept according to those groups. A bunch of priors, and then at the bottom here it got cut off. There's a likelihood statement, etc. So you don't have to start writing your STAN code with just a blank thing. You can use BRM to study how STAN code would get generated for like all kinds of different models, and just figure out what is the closest one that you want to estimate. Don't stop there, but start there with the code that Paul auto generates, and then you can start tweaking things around a little bit. Okay, that's all for today. I'll post homework tonight. It'll be due next Thursday, and then we'll talk about missing data next week. Yes?
So last time, I didn't get prior assumption. Prior, that was the case in this instance. You have the priors there, like the T. It's not show up, right?
Right. So the default, if you don't write anything, is just an improper or uniform prior over the sample space that you declare.
So that's what would show up.
So there would just be like no lines for the for priors on the coefficients if you're using an improper uniform prior. You just wouldn't add anything. It's equivalent to adding a constant, which isn't going to affect which draws get accepted. Other things like standard deviations across groups or whatever, those are going to have default priors. They tend to be half T and stuff like that in BRM. And so you're going to see lines for those. But definitely, like you can call set prior and then, you pass that result of that to make stand code, make stand data, and it will generate the stand code, and it has lines for those priors. Now you could change it afterward, but you might as well get it as close to what you want the first time. All right. Where's